All right. Hello, and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 6, 2025. We're kicking things off with this ICLR conference paper, Global Convergence in Neural ODEs, Impact of Activation Functions, published just over 3 months ago. This paper investigates how activation function choices, specifically their smoothness and nonlinearity, affect the training dynamics and convergence guarantees for Neural Ordinary Differential Equations, or Neural ODEs, focusing on the neural tangent kernel. Okay, so diving into the first set of results. Figure 1 here provides some numerical validation. Plots A and B show that, using the smooth soft plus activation, the differences in output and gradients between the neural ODE and its finite depth ResNet approximation decrease nicely as depth increases, matching that predicted $OL(-1) rate. Then, plots C and D illustrate how the empirical neural tangent kernel converges rapidly to its theoretical limit as network width grows. Building on that NTK convergence, these next plots look at width's impact. We see the smallest NTK eigenvalue stabilizes and grows with width, becoming positive, which is crucial. Then, parameter distances remain bounded, showing stability during training. Finally, the loss plots clearly demonstrate that wider networks converge faster and generalize better, driving both train and test loss down more effectively. This empirically validates the theoretical convergence guarantees for wider models. Okay, continuing with the theme of network width. Figure 5 here shows pair plots of the actual output neuron activations. We see plots for widths 10, 500, and 1000. Notice how as the width grows, those scatter plots become more circular. This indicates the neuron outputs are becoming increasingly independent of each other. It's another interesting property observed in the wide network regime, relevant for the convergence theory discussed earlier. So shifting focus now to the activation function itself. Figure 7 here directly compares a smooth one, soft plus, against a non-smooth one, ReLU. Plots A and B show that soft plus leads to faster convergence on both train and test loss, particularly noticeable in wider models. Plot C suggests more stable training for soft plus as parameters stay closer to their initial values. Plot D looks at the NTK eigenvalues. This really highlights the practical benefits of smoothness. Alright, now, Figure 8 shifts focus from smoothness to nonlinearity. It compares the non-polynomial soft plus activation against a polynomial quadratic one. Plots A and B clearly show that the quadratic activation leads to slower convergence on both training and testing loss across different network widths. Plot C indicates slightly larger parameter drift with the quadratic function. Interestingly, Plot D shows both have positive NTK eigenvalues, but the non-polynomial soft plus still performs better overall, highlighting the importance of sufficient nonlinearity. Okay, so figure 13 gives us a direct comparison between neural ODEs and ResNets, but this time using the non-smooth ReLU activation. Plots A and B show that both training and test losses decrease quite nicely, and similarly for both architectures across different widths. Plot C indicates the output differences stay small. However, look at plot D. The gradient differences oscillate quite a bit during training, suggesting potential challenges with non-smooth activations, unlike the smoother convergence we saw earlier. Okay, continuing the theme of activation functions, Figure 12 here directly compares the smooth soft plus and non-smooth ReLU activations. It looks at how the difference between a neural ODE and its ResNet approximation changes with depth, L. For soft plus, plots A and B show both output and gradient differences decrease nicely, matching that 1 per liter theoretical rate. But for ReLU, plot D shows the gradient difference remains roughly constant as depth increases, unlike the output difference. This really underscores the theoretical importance of smoothness for gradient convergence. So, wrapping things up, we've seen quite clearly how the choice of activation function really matters for neural ODEs. The key takeaway is that using smooth and sufficiently nonlinear activations like soft plus ensures the underlying dynamics are well behaved, training is stable, and we get those nice global convergence guarantees, especially in wide networks. This offers really practical guidance for building these models. That's all for this AI Research Roundup. Thanks for tuning in.